We can conclude our study of vectors and the three-dimensional coordinate system by looking at cylindrical and spherical coordinates. So we can form a cylindrical coordinate system by simply adding a third axis, a z-axis, to the polar coordinate system. So in the cylindrical coordinate system, a point in space is represented by the ordered triple r theta z, where r theta are the polar coordinates of the point's projection in the xy plane, and z is the usual z coordinate in the Cartesian coordinate system. So we can use our understanding of the polar coordinate system to develop following conversions. So if x, y, z are the rectangular coordinates of the point, r theta z the cylindrical coordinates of the point, then the conversion from cylindrical to rectangular, you have three equations. X equals r cosine of theta, y equals r sine of theta, and z equals z. To go from rectangular to cylindrical, we have the three formulas. R squared equals x squared plus y squared. Tangent of theta is equal to y over x, and z is equal to z. So we're going to convert the cylindrical coordinates 4, 2 pi over 3, negative 2 into rectangular coordinates. Right, so we're going from cylindrical to rectangular. So x is r cosine of theta, so 4 times cosine of 2 pi over 3. And cosine of 2 pi over 3 is negative a half. So our x coordinate is negative 2. So y would be r sine of theta, so 4 sine of 2 pi over 3. Sine of 2 pi over 3 is root 3 over 2. So we get 2 root 3 as our y coordinate. And z is the hardest of them all. This is just the z coordinate, negative 2. So we get our rectangular coordinates, negative 2, 2 square root of 3, negative 2. Now let's convert from rectangular, 1, negative 3, 5, to cylindrical. So r squared is x squared plus y squared. So we get 1 plus 9, which is 10, and so r is the square root of 10. Tangent of theta is y over x, so we have negative 3 over 1. Now, if we go ahead and we take a look, y is negative, x is positive, so that would be down here. This is where theta is going to be located. But remember, the range of the arctangent gives you values in here. Good, theta is already in the range of the arctangent, so we can just go theta is the arctan of negative 3. And z is just z. So our point in cylindrical would be the square root of 10, arctan of minus 3, and 5. So we now want to find an equation in cylindrical coordinates for each surface represented by the rectangular equation. So for x squared plus y squared is equal to 4z squared. Well, I can use x squared plus y squared equals squared right here. And of course, z is equal to z would take care of that one. So we have r squared is equal to 4z squared. And let's just leave it like that. Now for y squared is equal to x. So we're going to have to use y is equal to r sine of theta. That can be used there. X is r cosine of theta, which places there. So what we have is we have r sine of theta squared is equal to r cosine of theta. So r squared sine squared of theta is equal to r cosine of theta. We can divide by r, and we'll have r sine squared of theta is equal to cosine of theta. Now, if we do that, we have to make the restriction that r cannot be 0, which is a fairly safe restriction. So this implies that r is cosine of theta over sine squared of theta, which is equal to cosecant theta times cotangent theta. And so our equation is r is equal to cosecant of theta, cotangent of theta, as long as r is not 0. Let's now describe the surface given by the cylindrical equation. R squared cosine of 2 theta plus z squared plus 1 is equal to 0. Well, the first thing that we should do is take this cosine of 2 theta and use a double angle identity. So it's r squared cosine squared minus sine squared plus z squared plus 1 is equal to 0. Right, so we have r squared cosine squared of theta minus r squared sine squared of theta plus z squared plus 1 is equal to 0. R cosine of theta squared minus r sine of theta squared plus z squared plus 1 is equal to 0. Now we can use that x is equal to r cosine of theta here, and y is equal to r sine of theta here. And so this will give us that x squared minus y squared plus z squared plus 1 is equal to 0. So x squared minus y squared plus z squared is equal to minus 1, or y squared minus x squared minus z squared is equal to positive 1. Well, this is hyperboloid of 2 sheets. Right? We saw that in the previous video. It has y-axis, and it's centered at the origin. So in the spherical coordinate system, a point P in space is represented by the ordered triple rho, theta, phi. Right, so this is the Greek letter rho. You already know that one. And this is the Greek letter phi, where rho is the distance between P and the origin. So you can think of rho like the radius of the sphere. Theta is the same angle that is used to describe the location in cylindrical coordinates. And phi is the angle formed by the positive z-axis and the line segment OP. And this will give us the restriction then that phi is between 0 and pi. We can develop conversions for spherical in much the same way as we did for cylindrical. So we can look at this figure, and from this we can easily derive these conversions. The actual derivation themselves will be left to the viewer. So here are our conversions. XYZ is the rectangular coordinates. Rho, theta, phi are the spherical coordinates. So to go from spherical to rectangular, we have three conversion formulas. X is equal to rho cosine of theta sine of phi. Y is equal to rho sine of theta sine of phi. And Z is equal to rho cosine of phi. To go from rectangular to spherical, we also have three formulas. Rho squared is x squared plus y squared plus z squared. Tangent of theta is y over x. And cosine of phi is z over the square root of x squared plus y squared plus z squared. So let's convert the spherical coordinates 8, pi over 3, pi over 6 into rectangular coordinates. So we're going from spherical to rectangular. So x is rho cosine of theta sine of phi. So 8 times cosine of pi over 3 is a half. Sine of pi over 6 is also a half. So this is 2. Y is rho sine of theta sine of phi. So 8 times sine of pi over 3 is root 3 over 2. And so we wind up with 2 root 3. Finally, z is, so z, oh dear. Okay, we're just going to deal with that. Is rho cosine of phi. So we have 8 times cosine of pi over 6 is root 3 over 2. So z is 4 root 3. So our point is 2, 2 root 3, and 4 root 3. Now let's go the other way. Convert rectangular point 1, 1 root 6 to spherical. So rho squared, x squared plus y squared plus z squared. So we have 1 plus 1 plus 6 is 8. So rho is root 8, which is 2 root 2. Now, tangent of theta, y over x. I'm sorry, this was supposed to be a minus 1 in there. So the point should be negative 1, 1, root 6. So that should be negative 1 squared. There we go. So we have tangent theta is 1 over negative 1. Now, again, look at the coordinate system. Right, so the range of arctangent is quadrants 1 and 4. So if we look, our theta is given by a positive y and a negative x. Well, that's over here. However, taking the arctan is going to give us an angle in the fourth quadrant. So what do we have to do to go from the fourth quadrant to the corresponding angle in the second quadrant? We have to add pi. So this becomes pi plus the arctan of minus 1, which is pi plus negative pi over 4. So we have 3 pi over 4. Finally, cosine of phi is given by z over the square root of x squared plus y squared plus squared. Notice that's just going to be rho. So we get 2 times the square root of 6 over 2. A half times the square root of 6 over 2. So we get 1/2 root 3. So root 3 over 2. This means that phi is the arc cosine of root 3 over 2, and that is pi over 6. So our point is 2 root 2, 3 pi over 4, pi over 6. So now we wish to find an equation in spherical coordinates for the surface represented by the rectangular equation. So we know that x is rho cosine theta sine phi, so that takes care of that. We have y is rho sine theta sine phi, so that takes care of that. And then we have z is rho cosine of phi, and so that takes care of that. So what we wind up with is rho cosine theta sine phi all squared plus rho sine theta sine phi all squared is equal to rho cosine of phi all squared. So we have rho squared cosine squared theta sine squared phi plus rho squared sine squared theta sine squared phi is equal to rho squared cosine squared of phi. So we have a cosine squared there, we have a sine squared there. So this winds up being rho squared sine squared of phi is equal to rho squared cosine squared of phi. This gives sine squared phi has to equal cosine squared of phi with the restriction that rho cannot be 0. And again, that's a pretty safe restriction if we think of rho as a radius. And this will give us that tangent squared of phi has to equal 1 and rho cannot be 0. Finally, let's do the same thing for x squared plus y squared plus z squared minus 4z is equal to 0. Well, we can use rho squared equals x squared plus y squared plus z squared. Take care of that. And again, z is equal to rho cosine of phi. We'll take care of that. So we get rho squared minus 4 rho cosine of phi is equal to 0, which means that rho times rho minus 4 cosine of phi is 0. We have either rho is 0 or rho minus 4 cosine of phi is 0, which would mean that rho is equal to 4 cosine of phi. Now, take note. If phi is pi over 2, then rho is 0. So actually, this is a bit redundant. So we can take as that equation, rho is equal to 4 cosine of phi. So that not only concludes our study of the cylindrical and spherical coordinate system, but also our study of vector in three-dimensional space. We will next take what we learned here and now move it into vector functions. So instead of the vector components being constants, there will be functions of variables.